So do we have CL over CD in the sealing equation? Is it there? Is there leftover drag in the sealing equation? Do you have the slides? Shall I share it with you? Let me share with you the ones for sealing. Where is the sealing equation that we had in the at the very end? So the equation that we had that had the rate of climb, and we used it for the glide, and we used it for the sealing, didn't have L over D8, but what it had K and CD naught. Okay, so let me share that with you. L over D was important for the rate of climb. So if you are designing an aircraft that has to take off real fast and climb very fast, then you would worry about L over D. Then you should pick the airfoil that has the maximum L over D. But for the sealing, it was K and CD naught only, and K over CD naught, not multiplied by. So and so on. And today we are going to see different requirements for the range and endurance. So that's why we need to understand the effects of the different parameters on the performance before we start doing design. Question? Well, okay. Okay, so what we will be doing today, we will start looking at the range and what are the parameters that affect the range. We are going to derive the range equation. If you have taken AE 220, you did derive the range equivalent there, but we are going to do it real quickly here. Then we are going to look at the endurance, and the difference is that the endurance is the time flown by the aircraft, not the distance traveled by the aircraft. And we're going to see that there are two different requirements. Then we're going to summarize the equations of all performance we had, and we're going to solve some examples. Okay, so for the range equation, the question, what's the longest distance that can be flown by the aircraft? This is in feet if we are talking British units, or meters if we're talking SI units. And in order to do this, our starting point will be a very logical thing that, of course, the distance will be proportional to the amount of fuel you have on the aircraft. The more fuel, the further it can go. So fuel is very important. So we will look at how much the aircraft burns fuel, and this is defined by the specific fuel consumption. Let's start by a jet aircraft, where the specific fuel consumption, as you have taken in chapter 3, is the mass flow rate or the weight flow rate of the fuel divided by the thrust. W dot fuel over the thrust. This is how we defined it. Pound per second of fuel to pound per thrust. Now, some of you will realize that, well, we didn't have that minus sign before. Yes, we didn't have. It was fuel over thrust. But if I look at the flow rates or the burning rate of the fuel as the reduction in the total weight of the aircraft, then I will have that negative sign in here. So this negative sign means we are burning fuel. The total weight of the aircraft is going down. Okay. And why I need to do this? Because I will take this W dot and I will convert it to dW over dt, as it should be. Then I will take dt on one side and everything to the other side. Then I will take this dt and say, okay, if I multiply dt by the speed, that means I will integrate the speed with respect to time. This should give me the distance, and this is the distance I'm looking for. So the distance ds is the v dt. If I integrate this equation here, so I need first to replace the dt. So I'm putting it here from here into the equation. That's the dt that we have. And you will probably realize that we replaced the weight by the lift. We said the weight and the lift are the same thing, so I can multiply by L and divide by W because it's the same. And you probably realize that I replaced T with D because the thrust is equal to the drag. So Chi is replaced by D multiplied by L over W. I didn't change anything because they are the same. And that would be ds. So we made the range as a function of the weight of the aircraft. Here W is not the fuel weight, it's the weight of the aircraft. So how can I get S? Simple. I can integrate here with respect to W and I can integrate here with respect to ds. But I need to know 2 points on the function to do the integration. What does that mean? I will integrate ds from the very beginning of the flight to the end of the flight. From the very beginning, when the distance flown was 0, to the final when the distance is the range r. So that would be the limits on the left side. The limits on the right side would be the limits on the weight. What's the weight of the aircraft at the beginning and the weight of the aircraft at the end? Weight of the aircraft at the beginning, we are going to call it W naught. That means it's the total weight of the aircraft including fuel. And at the end, the weight of the aircraft, we're going to call it W1. That's with the whole weight of the aircraft without the fuel because it's burned now. So integrating here between 0 and R, integrating here between W1 and W0, or W0 and W1, will give me the range that I have. You will realize that we took the minus sign with the consequence of switching the limits of the integration. I should have integrated from W0 to W1, from the initial weight to the final weight. But because of the negative sign, we flipped the limits of the integration to W1 to W0. Speed, L over D, CT, all these are numbers, constants I can get out of the equation. And the integration of dW over W is simply len. And when you substitute the limits, 1 and naught, it will be len W0 over W1. So that would be the range of a jet aircraft. If you want to maximize the range of this aircraft, you can maximize what? In here. What would you change in order to increase the range of aircraft? Now we're talking design. Okay, so I need you in the chat or the conversation, just write one sentence, including what would you do to increase the range of an aircraft? Increase the range of an aircraft, this is a question like you get in a quiz or a homework or something, but in reality, in design, we want to achieve the range of the aircraft. So if you want to achieve it, what parts of the design you have to worry about? You have to increase, decrease, improve. What would you do? From the equation, just write one sentence in the chat box. Nothing? Okay. Increase L over D ratio, that makes sense. So increase L over D in here. So you have to pick the airfoil. Now to the question that was actually we design the airfoil. Yes, we will pick, if the range is the most important thing in your design, then you will have to pick the airfoil that had maximum L over D at cruise speed. Okay, that's one thing. The other thing, decrease the drag. Well, drag does not appear here by itself. Drag is as the ratio. Decreasing drag by itself will not help if L goes down as well. So again, the objective is to increase L over D. Another thing that you wrote, increase W naught over W. Yes. What does that mean, increase W naught over W? As a designer, what should I do? How to increase the initial weight of the aircraft compared to the final weight of the aircraft? Physically, what does that mean? It's not like an equation, I'm going to put a larger number. In the design, what shall I make? I'm asking here Fahd Al-Qahtani who wrote it. So to increase W naught over W1, what does that mean? You are the designer. What will we do? Initial weight compared to final weight, and you want to make it larger. So what do you do? Well, okay. What's the difference between W naught and W1? What is W naught minus W1? Yes, W fuel. It is fuel. So if you want W naught over W1 to increase, simply put more fuel on board the aircraft. Use larger fuel tanks, make more room for fuel, and add more fuel. Okay, so that's the second thing we can do here. Put more fuel on board the aircraft, improve L over D, and the last thing mentioned here by Amin is to pick the engine that has the least specific fuel consumption, CT. So these are the three things we can do. More fuel, airfoil that has CL over CD max, and engine that has lowest CT. Okay. Now let's look at this more closely. Let's V. I can take off V here, and you will be surprised that the answer that we had of L over D might be changed. I was expecting one of you to say this. V is not just a number. It depends on the CL, because 1/2 rho V square SCL is equal to the weight of the aircraft. So V is actually the weight divided by 1/2 rho SCL. So V has a lift in it. V has CL, just like this is CL over CD. V here has one CL in the denominator. So when I replace V with the expression of 1/2 rho S, it will take 1/2 of that CL on the top. So it will no longer be CL over CD. It will be CL to the power half over CD. Do you see where did this half go away? Here the power was 1, but 1/2 of it will go when I substitute for V to equal the weight over 1/2 rho SCL. So I will cancel root square CL with one of the root square CL, so we will end up with this. So again, now the equation is more clear. I should have looked at this one, not the previous one. So you guys, Fadil, for example, it's not CL over CD that matters. It's CL to the power half over CD that matters. This is the one we need to maximize, and it's not the same. It's not the same. The maximum this is not the same as CL over CD. And if you are not sure of this, if you don't see this, look at the formula sheet we had in the quiz. We had an expression for the maximum CL half to the CD and an expression for the maximum CL over CD. And there was even an expression for maximum CL to the power 3 over 2 over CD. They are all different. Okay. So in order to maximize, put more fuel in here, use lower CT engine with better performance, less fuel consumption, and use an airfoil that has the maximum CL to the power 1/2 over CD. And this depends on the wing. Any questions? Okay, so that's for the jet aircraft. Now for the propeller aircraft, it's the same thing. So we're not going to do the same procedure, except that the specific fuel consumption is not the weight divided by the thrust, the weight of fuel divided by thrust, but it's the weight of fuel divided by the power. And we will do the same thing. But once we have power in the equation, that means I should have velocity also, and the velocity will cancel the V that I have. You see, when we had T, we ended up having V in here. If this was power, then it will have T times V. So the V will disappear. So when the V disappear, you will find that it's L over D that matters, not L to the power 1/2 over D. So for a propeller aircraft, that would be the equation for the maximum range. Very much similar to that of the jet. You will see the weight ratio, you will see L over D, but you will not see the velocity, and you will see C related to horsepower, not related to thrust. Okay, L over D maximum here occurs when, this is from the formula sheets that we had in the midterm or from chapter 2 aerodynamics. CL over CD maximum is 1 over 4 CD naught K. That's why the drag polar is extremely important. Remember, this CD0 was like 0.01 or 0.02, this one was 0.04, very small values. But you see, these small values is what determines the L over D maximum. And L over D maximum determines what's the maximum range for a propeller aircraft. So drag polar is extremely important, and slight variations in these small numbers will greatly change this value and greatly change the range. So this equation for range of a propeller aircraft and this one for the range of a jet aircraft. You can use this one or that one. They are the same, the ones in the red frame. These two equations are identical except that we replace the speed with this expression. Okay. Now to the final question we will answer in this chapter, which is the endurance. Endurance is the time flown by the aircraft. So I don't care about the distance, I care about the time. To get the distance, we integrated ds. To get the time, I will integrate dt directly. Okay, so we will integrate both sides between 2 points. Initial point when t is 0. The weight was the full weight of the aircraft with the fuel, and when the time is equal to the endurance, that's the flight time. The weight is the final weight, which is the initial minus the fuel. And if I do so, and I will integrate just like we did in the range, I will get this expression for the endurance. It has the weight ratio, same thing. It has L over D, same thing. It does not have velocity in here because we're using time, not the distance, so the velocity will disappear and it will have the CT. So to improve the flight time of a jet aircraft, put more fuel, pick the airfoil that has maximum CL over CG, and use the engine that has the lowest fuel consumption, CT, thrust fuel consumption. Okay. And I don't need to tell you that we will do the same for propeller. Exactly the same thing for propeller, but this time this will be power. Power will give me speed. Speed will give me CL to the power 1/2. So instead of CL over CD, you will find CL to the power 3 over 2 over CD. That's the third ratio we had in the formula sheet in the midterm. So now there are 3 important aerodynamic ratios. And as a designer, you need to know what do they affect. What do they affect? You see, this one, root square CL over CD, this ratio is what determines the range of a jet aircraft. Range of a jet aircraft. Then we have CL over CD, no halves in here. This ratio affects the range of propeller aircraft and affects the endurance of jet aircraft. If the aircraft is propeller, it will determine the range. If it's jet, it will determine the endurance. And finally, the third ratio, CL to the power 3 over 2 divided by CD. This one is what determines the endurance of propeller aircraft. So that's why these 3 values were important. That's why there were equations for them in chapter 2. And when you asked why are these important, you solved one homework where you found the maximum of this value. I told you, wait, it will affect the performance of the aircraft. Any questions up to this point? Now that's the last equation we're going to have on chapter 5. This is the last performance equation that we have. I just want to summarize from a design point of view what are the effects that we have discussed. So when you need to satisfy a certain range or endurance requirements, because we will start with the requirements in chapter 10. We will put some requirements and we all will go through the requirements to achieve the design. If you want to satisfy a range or endurance requirements, here are the three things that you need to do. Put more fuel. So you will see some designs, some airplane designs have certain large fuel tanks. Maybe the whole aircraft will be a flying tank, just like this one. You have here a fuel tank, fuel in the wing, fuel in here. It's almost a flying fuel tank. Okay, you will have other aircraft will have smaller fuel tanks because range is not an issue. It's not required to have that much of fuel. So if the range is an issue, the first thing to do is to put more fuel. Now this Voyager achieved the endurance limit for an aircraft which was 9 days and 3 minutes. Now in order to do this, they must have selected, when you go to endurance propeller, they must have selected an airfoil that has the maximum value of this ratio, CL3/2/CD. And this ratio is determined from the drag polar. If you know CL, you will get CD. So depending on the drag polar, you get this ratio, large fuel tanks, and you have high endurance. The second thing is to pick the engine with the lowest CT or C, depending on whether it's propeller or jet. C when it's propeller, CT when it's jet. So just have to have a feeling of the range of this specific fuel consumption, because you will have to pick a type of an engine. Let's have a look at all these families. On the vertical, we are having the C, the fuel consumption. You can call it CT for the turbojets and turbofans, and even here. And you can call it C, only C for the turboprops and internal combustion engine. And you can see that a turbojet is just like a turbofan, but with a bypass ratio of 0. What's the bypass ratio? Anyone say what's a bypass ratio? Chapter 3, jets, turbofans. What is the bypass ratio? Yes, Mu'taman.
I think it's the air, cold air over the hot air.
Yes, the air that goes through the fan, if there is a fan, over the hot air that goes through compressor turbine. Turbojets, since they don't have a fan, then the bypass ratio is 0, right? So for a turbojet, the specific fuel consumption is about 0.9. That means for every pound of thrust, you need to burn 0.9 pound of fuel every hour. The unit here is per hour. The numbers here per hour. So if the engine has a thrust of, let's say, 10,000 pounds, you need to burn 9,000 pounds of fuel every hour. Okay, so that's what it means. If you have a turbofan with a low bypass ratio, that means a bypass ratio less than 1, that means the fan is small. It's not a big fan, the fan is small. It's a little bit greater than the compressor diameter. So in this case, the specific fuel consumption will drop from 0.9 to maybe 0.8 or 0.75. That's good. The lower the better. Remember, the lower C here, the better in terms of endurance and range. So that's good. Now, if you have a high bypass ratio, that means the fan's large fan, bypass ratio 6 to 8, typical transport aircraft now flying in this range, you will see specific fuel consumption will go down. All these are types of engines that are actually flying Pratt & Whitney 2000, 4000, 480. Now you will see they have a specific fuel consumption in cruise of around 0.6 or 0.55. Now, on the extreme, if we increase the diameter of the fan compared to the diameter of the compressor and make it a very large, maybe a bypass ratio of 15, that means 15 kilograms of air would pass every second in the fan for every kilogram of air that goes and burns the fuel. If we do so, we call this a prop fan, and in this case, the specific fuel consumption will go down even to maybe 0.48. Finally, a turboprop will have a propeller and you don't have the duct in here, will have a very low specific consumption. We're talking about 0.45. So depending again on the range and the speed range of the aircraft, you will pick the type of propulsive system when we get to chapter 7, 8, and 9. Any questions in this chart? The last thing we talked about, put more fuel, pick the low C, and the last thing was to maximize the ratio. Sometimes the ratio is CL over CD, sometimes it's CL to the power 1/2 over CD, sometimes it's CL to the power 3 over 2 over CD. Okay, so pick the airfoil that gives you this, the maximum ratio, appropriate ratio. And when I say appropriate, the ratio changes between jet and propeller, between endurance and range. Pick the airfoil that gives you the maximum ratio at the flight condition you want. So for example, what you see here is the lift over drag for 3 types of airfoil, 0012, 18, 25. Each one of them will give me a certain value of L over D. And you will realize that here L over D is higher than this one, than that one. But the maximum occurs at a different angle of attack. The horizontal is the angle of attack. So the maximum for this one, the green curve here, is at 5 degrees. For the red curve is about 6.5 or 7 degrees. And for the blue one, maybe it's around here, like almost 7 or 8 degrees. So depending on the cruise speed, I can determine the angle of attack. Can anyone tell me how from the cruise speed I determine the angle of attack? Because I know the angle of attack, I will pick the airfoil that has the maximum value at this angle of attack. Now I'm going to stop for a second and see if you guys remember stuff from chapter 2. If I give you a cruise speed and you do your calcs of the A in chapter 2, can you get the angle of attack?
Yes, we can.
Okay, how are you going to do this? Here is the cruise speed, 400 feet per second. What would you do to get the angle of attack? Okay, let's divide them into steps, just like we do in quizzes online, where we have to divide it into steps. From the speed, can you get the CL? Yes, the CL is equal to the lift or the weight, because they are the same, divided by 1/2 rho V square S. So that will give me the CL. And if I have CL, you already know that CL is equal to the A times the angle of attack. CL is equal to the slope times the angle. So you will get the slope A and you will get the angle of attack. So yes, knowing the cruise speed, I can get the angle of attack and I will pick the airfoil that has a maximum value of CL over CD at this angle of attack. Okay, so now we'll start to relate the performance. Performance is simply the equations that we have in here with the design. What should we do? Use more fuel tanks, lower C engine, and pick the airfoil, the minimum of L over D. Okay. Okay. Let's try to put some numbers in there. Example 519 says for the Gulfstream 4, the aircraft that you are very familiar with, flying at 30,000 feet, calculate the range and the speed at which this range occurs. So we need R and V for this jet aircraft. Knowing that the fuel mass or the fuel weight is 29,500 pounds, and the specific fuel consumption, thrust specific fuel consumption for the engines are 0.69. Now you should start to develop some sense of the numbers so that you can judge when you see a number if it makes sense or not, so that when you make mistakes later on in a homework or a quiz, you can go back and say, no, that value doesn't make sense. I need to revise that. 0.69, you see, 0.69 here, it would be somewhere in here. Now that's a turbofan, so yes, it is within the range. It's within the range. It's not very high, it's not very low. So we know C, but we know it per hour, not per second, the burning fuel per hour. We know the amount of fuel, and we know the aircraft. So, and it's a jet aircraft. So I need to find the range. So here is the range equation. You don't have to memorize them. That's this range of a jet aircraft that we derived today. The one that has the weight ratio CL over CD, S, and C. Now, for the ratio of the CLs, I need CL to the power 1/2 over CD, and we had a formula for that. And from the formula, you solve it as a homework. For this particular aircraft, the value turned out to be 25. So we know this, and this was a function of, remember, K, CD naught, and so on. So this gives me 25. For the initial weight of the aircraft, we know it to be 73,000. We have solved so many problems on this aircraft before. What about the final weight? Well, the final weight is the initial weight minus the fuel, and it's 43,500. So we know this one. Finally, C in here is given in the problem per hour, but we need it per second. Always we are converting to the standard unit in the British system, which is the second. So in order to convert it to per second, I'm dividing by 3,600. So that's the weight of fuel per second in order to get 1 pound of thrust. Of course, the density is the density at 30,000 feet. The wing area is known for this aircraft, so all the numbers now we have it. Turns out to be the range is 24.7 million feet. Okay, 24.7 million. How do I know it's feet? Because I used all the standard units. I used the weight in pound, I used the density in slug, I used the CT per second, so the range is in feet. So if you want it in miles, for example, of course you can have it in kilometers if you want, convert from feet to kilometer, but typically we put it in miles. So convert it from feet to miles, that's the conversion factor, 5,280. Now, what I can promise is that you will not be converting from one system to the other. You will not go from SI. No need to do that. Typically, the whole aircraft is designed in one system. But you might want to convert like only these two things from here, from second to hour or hour to second, or from feet to miles, and sometimes from feet per second to knots, because the knots is a very famous speed unit. So you need to have these either three numbers in mind or just write them down. Conversion from feet to miles. I think in the textbook there is some of you when you're even mobile or calculator will have conversion right away. Okay. So the range 24 million feet. This aircraft can fly 24.7 million feet. That's 4,680 miles. But in order to get this range, you must fly at the speed that's used here, the speed at which CL to the power 1/2 over CD is maximum. And again, we have an expression for that. It is in your formula sheet for the midterm. When you calculated this ratio, and it occurs at this speed, and you also did it in the homework. So this speed, also a function of K, CD naught, S, and so on, turns out to be 830 feet per second, and that's at 30,000 feet. So the range is 4,680, but in order to do it, you must be flying at 566 miles per hour. If the aircraft flies at slower speeds, let's say 550, it will not achieve that range. It will fly at faster speeds, let's say 590, it will not achieve that range. It will be both case lower. Just like your car. If you want to use to get the maximum range of your car, you should drive the car all the time at 90 km per hour, the economic speed, if it's 90 or 92. Okay, if you drive at 80 or 100 or 120, you will not achieve the maximum range of the car for a given amount of fuel, of course. Okay, any questions in the example? Okay. Now, these questions are kind of, when I say any question, I guess there's something that bothers me. I get more questions in the section at 9 o'clock than the question at 10 o'clock. Well, statistically, that cannot happen because you are double their enrollment. So statistically, I should get more questions here. So there is a couple of explanations for this. Maybe since, I don't know, since I recorded the initial lecture and you have seen it, it's, well, we know, let's think about it later. We have the lecture with us, so let's watch it later and have questions later. That's maybe one explanation. Or I'm not having all of you here. So how can you explain this? It really is like bugging me.
I think the student at 9 o'clock, they now taking AA 220.
Okay.
So they didn't cover this part in AA 220.
That makes sense. That makes sense. Yes, because they are the one that registered afterwards, freshman and sophomore. Okay. So for you guys here, if you feel that I'm going slower than, well, as it should be, because if you have taken, most of you have taken 20, just let me know. We can go a little bit faster. Okay. Although starting by Wednesday next week, actually that's going to be a whole new thing for you. Okay, thank you for the explanation. So for the second example that we have for the endurance, the question says calculate the flying time, maximum flying time or maximum endurance for this Gulf Stream using the same information that we had. So it's a jet aircraft endurance. We have an equation for endurance that has the weight ratio, L over D, and the specific fuel consumption. We have the weight, we have the specific fuel consumption, but be careful here. This is L over D, not L to the power 1/2 over D, and the maximum is different. That's why in the homework, when you solved in the quiz or in the midterm, there was like different values, different expressions for the ratios. So here it's CL over CD, and it's a different expression, and it will be 14.4, not the 25, but will be 14. So when I do so, the endurance turns out to be about 39,000 seconds, and the unit here is the second. Of course, you don't have to worry about the unit here, no units. Here, no units, it's only the C. So since C is per second, you will get E is per second. So E turns out to be 39,000 seconds, about 10.8 hours. Now, let me ask you a question. What would be the speed that should be flying to get that endurance, 10.8? Is it that speed, 566 miles per hour? My question again, to get the endurance limit or the maximum endurance, the maximum flight time, should I fly at this 566 miles per hour that we calculated before? Yes or no, and why? Different speed. It will be different speeds. Okay. And why is that? This speed 566. Okay, thank you, Amin. It's a different speed, and the reason for this is that this 566 is the speed at which CL root square CL over CD is maximum. Okay, and that was okay for the range, but here we want CL over CD. So the speed is different. Here is the speed for L over D maximum. That's the speed. And we calculated in a previous example, just last lecture, we calculated it when we were talking about climb and glide and so on. So the speed is 631. So if you go 631, the airplane will be flying for 10.8 hours, but it will not go for 4,680 miles. It will be a shorter range. But if you fly the aircraft at 566, you will fly for 4,680 miles, but this will take less time than 10.8. It will not be 10.8. Does that make sense? So yes. You go slightly, yes. So if you go faster, you will cover more distance, but the time will be shorter. If you go slower, you will not cover as much distance, but you will stay airborne for a longer time because you are not burning that much of fuel. So that's why range and endurance are different, and every aircraft is optimized on maybe one of these. Some aircraft wants to fly longer and one wants to fly for a longer time. Okay. So with so many equations, today we have like how many? We have 8 equations. One equation for the range and one for the speed of it, and one for the endurance and one for the speed of it. And then we have another 4 for the propeller aircraft. And we had equations last time for the ceiling, rate of climb, and so on. So many equations in chapter 5 that it starts to get confusing. For this, if you turn over your textbook to page 314, we have a summary in 3 pages, 314, 15, and 16, on the equations. And what are these equations for? So we have, for example, range of a propeller, range of a jet, endurance propeller, endurance of a jet, V speed, V maximum, CL, and so on. We have, these are only sample of the equations. You see, these are not all the equations. You have 3 equations. Think of these 3 pages as like the formula sheet of chapter 5. When you solve the homework, that's going to be posted today, inshallah, our third homework, you will probably want to have a look at this summary before you start flipping in the textbook. It will tell you right away where to go and which equations to choose. So today we've finished the steady flight, everything that has to do with steady flight, chapter 5. Next time we will do accelerated flight. Wednesday and Monday, accelerated flight, takeoff, landing, and turning. And we will also see what performance characteristics are important for this, for the design of a jet and propeller aircraft there. Wednesday next week is going to be a very important lecture where we are going to say, okay, we are done with the performance, we are done with the basics. How do we proceed with the design? There are so many constraints, so many things. That will be departing from the E8 to 20. That's where we are going to have, okay, let's make a roadmap where to go. That's on Wednesday. And on Monday of week 10, that's when we're going to start doing the design. I will announce the design project and we will follow the procedure that we present in chapter 7. And as we go, we will learn new things in chapter 8 and 9 on the design of propeller and jet aircraft. Okay. Any questions, Isra? Okay.
Thanks, Dr.
So, inshallah, I will see you on Wednesday.